Okay, so I'm going to do this a little early this morning. I'm going to get this done. Quizzes I sent out this morning. The results. Do your quiz corrections if you want them. Um, Not too bad. They weren't too bad. Um, if you haven't done your quiz review, which there's a few of you that I have not seen, I think the same three that I emailed last night evening about not having your quiz done. You know who you are. Those three need to turn in their quiz 2 review that I sent out. Um, so, yeah. Anyway, all right. So here we go. We are gonna go to. We're gonna start to finish up this last section here. You know, this will be the last chapter that we do for anatomy. So we will work our way through this. There's still quite a few slides here, so we're going to go through some stuff here. Okay. So when we talked about the 4 steps. We talked about pulmonary ventilation, external respiration, the transport, and then the internal respiration. Well, here we're going to talk here about the gas exchange in the body. And so as we look at this, we have some different laws here that we have to go. Now we did Boyle's law, right? We did the one where pressure and volume um, are inversely related. Um, so hold on, I gotta do this. What did you? So here we go. Dalton's law. So let's go on to Dalton's law here. Okay, well we talked about Boyle's law, right? If we increase the volume, we decrease the pressure. If we decrease the volume and squeeze it down, then we increase the pressure. All right, so that was part of that pulmonary ventilation here. Now, when we get into Dalton's law, it's used to determine the individual pressures of each gas in a mixture of gases. All right, so now we're talking about the individual pressures within something. Okay, so it's based on a percentage of total of millimeters of mercury and atmospheric pressure. So, um, yeah, so as we do that, so now as we look at this, so atmospheric pressure, the majority of it is nitrogen, and then we have a certain amount that is oxygen, and we have a small amount with is argon and carbon dioxide. Okay, so it's used to determine the individual pressures of each gas in a mixture of gases. Okay, this Dalton's law is. Okay, so the gas exchanges that occur. Okay, so we have these gas exchanges that go between the blood and the alveoli, right, which is the external respiration, right? So, I mean, technically, what's the alveoli, what's the air inside the alveoli is outside the body, if you think about it. So, inside to outside, so that's your external respiration, is your inside to inside, so your internal respiration between the blood and the tissue cells. And this takes place by simple diffusion, right? So, simple diffusion is going from high concentration to low concentration. So, sorry, I'm trying to do 2 things at once. So here's how we do this, right? So simple diffusion. So depending on the partial pressures of oxygen and carbon dioxide that exist on opposite sides of the exchange membrane. All right. So this kind of depends on the pressure of oxygen and carbon dioxide on this semi-permeable membrane, this simple squamous alveolar, right? Or if we're talking about internal respiration between the blood vessel wall and the tissue, right? And so we're always flowing from high to low pressures, right? So if outside is a high level of oxygen, high pressure, and inside is a low pressure of oxygen, the oxygen is going to travel inside. If it's carbon dioxide's high on the inside and low on the outside, carbon dioxide is going to push its way out, right? Those pressures are going to equalize, right? So anyway, so it's always flowing from high to low. Okay, so we got to remember that. So we have these partial pressures, right? And when we're talking about whether we're in an alveoli or a blood vessel and tissue, if there's a high pressure in the tissue and a low pressure in the vessel, that whatever that is going to move from the outside to the inside. Okay? Sorry, I have all kinds of noises going on today. Apparently, everybody needs to get a hold of me when I start my class. So let's see. Henry's law. So Henry's law states that the solubility of a gas in a liquid, okay, how readily a gas is in a liquid is directly proportional to the pressure that gas above the surface of the solution. All right, so the higher the pressure of the gas, the more gas that will be shoved into the liquid, thus increasing the solubility. All right, so if we have a half gallon, if we take a container of a gallon of milk container, and we put water in half of it, and we have air in the top of it, and let's say we're going to use pure oxygen. The way that we can get more oxygen into that water would be to increase the pressure above the water and drive it into the liquid. Does that make sense? So, how soluble the gas is in a liquid, right? So how we get the gas in a liquid is that we have to increase the pressure at the surface of the solution, right? So we jack up the pressure in the space above the water, and the higher the pressure, the more of that gas that will get driven into the solution. That's Henry's law. Does that make sense? So when we talk about that, here we are, right? We have our solution down here. We have our gas up here. If we increase the pressure, or increase the amount, we increase the pressure. That's what it's doing, right? So this is kind of like Boyle's law, right? You decrease the volume and you increase the pressure. So if we increase the pressure, we're going to drive those gas molecules into the solution. Okay? So the solubility of a gas and partial pressure have a direct relationship, right? So the higher the pressure, the more soluble. The lower the pressure, the less soluble the gas is in that solution. Okay? These are directly relationship, right? Boyle's law is inversely relationship, right? The greater the volume, the less the pressure. The smaller the volume, the higher the pressure. All right? So you're going to have to get these straight. Okay? So when we talk about solubility coefficients, right? This coefficient of the gas affects this process, right? So some things are more soluble than others, all right? So the higher the number, the more the gas likes to dissolve into a liquid. So it's based on the structure, all right? So when we look at these numbers, carbon dioxide is the most soluble molecularly, right? Just the molecular structure of carbon dioxide allows it to be more readily absorbed or more soluble into a liquid. Okay? Each gas will dissolve in a liquid in proportion to the ratio between its partial pressure gradient and its solubility coefficient. All right? So there's a whole bunch of stuff going on here, right? You've got, not only do you have like that whole high to low thing, but you also have the solubility coefficient, right? So not only do we have to drive it in, but we also, if it just molecularly wants to be dissolved. All right, so there's a whole bunch of different things here, right? So when we look at this, carbon dioxide is readily, it's twice, way more than that. It's way more soluble than oxygen. And oxygen is twice as soluble as nitrogen. Okay? So the molecular structure here allows for readily dissolving in fluid or solution and not so much. Okay? This is a lot of like physics stuff, right? Anyway. So the second law of thermodynamics, right? Solubility and temperature have inverse relationships. All right, so now here we are, opposites again, right? If we increase the temperature, it causes an increase in the energy, kinetic energy, causes the molecules to move around faster, which allows molecules to break the intermolecular bonds and escape from solution. All right, so we're talking about solubility. We're talking about something that is dissolved in a fluid, in a solution. If you increase the temperature, everything speeds up, bonds will break, and stuff will escape out of that solution. Does that make sense? We can see that, right? We see water boiling, and we see that kind of stuff, right? And so we see as stuff will escape solution. All right. Now, if we cool it down, if we cool the temperature down, that's going to cause everything to move slower, which the bonds will not break, and therefore we will have very little bit of stuff flowing out or dissolving out of escaping the solution, right? So ozone solubility and temperature. All right. So here we have water. We have high temperature. We jack the temperature of water. All the molecules move around more. The bonds are broken. And all of a sudden we have the ozone gas that is dissolved out and it escapes the solution due to the high kinetic energy, all the molecules moving fast and moving around and breaking bonds, and they escape the solution. Okay. On the other hand here, if we take water and we cool it down, this energy is slower, and therefore it is not going to break bonds, and it will be able to hold stuff in, and also looks like even, what does it say it's going into? It's going into solution. Okay. So there's a lot of laws here, right? There is Dalton's law, right, which is figuring out how much of each gas is in this atmospheric pressure, right? The partial pressures. So when you take 760 millimeters of mercury, 78% of that pressure is nitrogen, 20% of that, or almost 21% of that is oxygen, almost 1% is argon, and the rest is carbon dioxide. Okay, so that's Dalton's law. When we get to Henry's law, we talk about the solubility of the gas, of a gas being able to go into a liquid, is based on this pressure, right? If we increase the pressure, we will drive more stuff into the solution. Or if we increase the if we increase the pressure, we drive more stuff into the solution. If the pressure is not as great, then the tendency is that it will not have as much stuff dissolved into it. Okay, and then we get into the solubility coefficient. That basically what this is that the molecular structure of these gases lend itself to be readily soluble or not as soluble. Okay. The second law of thermodynamics: if it's hot, if you increase the temperature, you're less likely to get things to stay into the solution because things are being moved fast and they are breaking bonds. If we cool the solution down, we're more likely to keep gas dissolved in the water or solution because the kinetic energy is low, things are not moving around that much, bonds are not being broken. Okay? All right. So let's all right, so let's just do this one and then we may be done, just because we've had a lot of laws and rules in inverse and direct. All right, partial pressure gradients and gas solubilities. Okay, so partial pressure gradients, right, and gas solubilities. All right, so oxygen has low solubility but steep partial pressure gradients. All right, so we have a pressure of 105 millimeters of mercury in the alveoli. Okay, and we have a 40 millimeters of mercury of blood, which is way lower. Okay, which is way lower than the alveoli, right? So we have this high in here, we have this 105, we have 40 here. So that oxygen travels from high to low. It is going to travel into this vessel, right? So here we have that part, that external respiration. We have this partial pressure gradient difference, right? Now what we see here we have this difference, right? Now what we're seeing is that we exchange that. So now in the blood we have oxygen at 105 and carbon dioxide at 40. We have this switch, right? Now we're carrying around oxygenated blood. Okay, so we see that difference, right? That's that high pressure to low pressure. So oxygen is going to go from the alveoli into the blood. Okay, carbon dioxide has a solubility 20 times greater than oxygen, but partial pressure gradient is only 5 millimeters of mercury, right? So here we just see that we have this carbon dioxide is readily soluble, but the pressure is less. And so what you're going to see is, as this moves through, you're going to see this switch here. So we're only going to have an exchange of 5 millimeters of mercury. So we're going to have carbon dioxide that floats around at 40, and then this oxygen is going to be at 105 as it travels through. Now, as it goes through the whole system and things start to use it, right? Now we have tissue cells that have partial pressure differences, right? So this cell here needs oxygen. So this oxygen is going to travel into the cell. This cell has lots of carbon dioxide. It's going to exchange some carbon dioxide into there, and then we switch, right? Now we're back to this whole 40, 45. Now that's deoxygenated blood, okay? Simple diffusion, high pressure to low pressure, okay? So here on the deoxygenated side, we have a higher carbon dioxide and a lower oxygen, and so that's going to switch, okay? Pressures from high to low, and we have that gas exchange, okay? As that is carried out through, once it reaches a tissue that uses the oxygen and needs the oxygen, that oxygen gets exchanged. The oxygen goes in, the carbon dioxide comes out, and now we have essentially deoxygenated blood that needs to travel back to get reoxygenated. Okay, so that was a lot. That was a lot today. Okay, so you just need to make sure that you understand these laws, the partial pressure stuff, right? Where we're taught this whole thing of this thing right here, that right here, that slide is this slide right here. Okay? Always flowing from high to low. All right. Henry's law, again, the solubility of the gas bases on the pressure, right? A high pressure outside of the solution is going to drive it in. A low pressure, things can escape, right? And then you talk about solubility coefficients. The carbon dioxide is way more soluble than oxygen. It is a molecular thing. It is just the way the molecules and the atoms are arranged allow for things to be highly soluble or not. We talk about the temperature. The higher the temperature, the more kinetic energy, which means the less amount you're going to be able to keep in there because you're going to have bonds that are breaking. But if you cool it down, the tendency is for the solution to hold the dissolved gas because the movement, the kinetic energy is low. The bonds are not being broken. Okay? So this looks hard, but if you always look at everything here, I mean, we have the exchange here and we have the exchange here. We have external respiration and we have internal respiration. It is just traveling from high to low. Carbon dioxide is traveling from high to low. It is taking carbon dioxide out of the blood, putting it into the alveoli to be exhaled. And so when these are holding oxygen, we have a high level oxygen to a low oxygen. It's going to go into the blood. That's going to switch those partial pressures, and now we have a blood that is full of oxygen and less of carbon dioxide. That is going to go around the body. When it finds a tissue that needs it, the the pressure of oxygen is going to push into the cell. The carbon dioxide is going to push out of the cell from high to low here, right? And now we have essentially deoxygenated blood that is going to travel back. It's not that difficult. This is a pressure thing, all right? So you have to make sure that you understand this, all right? We'll keep going tomorrow. Get your review sheets in, and make sure you do your quiz corrections. All right, guys. You guys have a good day, and I will. If you have any questions, you make sure you call me or email me. Don't call me.